Hello, and thank you very much for the introduction, attending. As said, my name is Matt Hamilton. I'm the Principal Developer Advocate at Protocol Labs. One slight caveat is that I've got a little bit of a cough at the moment, so hopefully I won't be coughing through this, but just give me a sec if I do here. So, while some of you might not have heard of Protocol Labs, you've possibly heard about the protocol that Protocol Labs is most well known for, which is called Interplanetary File System, or IPFS. If you've had any involvement with NFTs, you might have seen IPFS referenced in that and wondered what it is. So today I'm going to talk a little bit about IPFS, explain what IPFS is, and why you should be using IPFS for storing the data for XLS20 NFTs on the XRP ledger. But first of all, let's just talk a little bit about IPFS in general and just widen the scope a little bit. First of all, why are we here? This is a quote that comes from a talk given by Juan Benet, the founder of Protocol Labs, and explains a lot about the motivations and the why behind what it is we do. As the technology that we use evolve, then the control of that technology becomes more and more important. Here at Apex, we're interested in the Internet of Value and the flow of value in a decentralized, permissionless, censorship-resistant way. At Protocol Labs, we're interested more specifically in the storage and transmission of information and data, and how that works in a wider sense. What good is having decentralized applications running on a blockchain if the user interface or the data that it references is stored in a centralized system and becomes unavailable? What about if we could store data for public good that could be accessed by people worldwide? Things like machine learning training data or open science research data. I was actually talking a couple of nights ago here at Apex with John, who's here. He's a campus ambassador with the XRP Ledger Campus Ambassadors Program, and he's a PhD geologist. And he was talking about the amount of data that comes out of geothermal energy studies that they do. Wouldn't it be great if we could store that data in something like IPFS and make it available for anybody to access? So let's get a little bit into the tech details about IPFS. IPFS, as I said, stands for the Interplanetary File System. But the name is more than just a meme. It's a distributed peer-to-peer network for files and folders, and it was designed to be able to work even across space, even between planets. Let's say you've hopped on a shuttle SpaceX rocket over to Mars, and you're currently living on the red planet, and you want to request a file from Earth. That might take an hour for that file to transmit across space. But if there's somebody local on Mars that already has the file, then IPFS would allow you to download that file seamlessly from them rather than waiting and requesting it, so you get it instantly. So we're thinking ahead here. At this point, it may sound like just a fancy way to describe a peer-to-peer network, and it is, but there's some real power behind IPFS and the way it works and what it enables. There's no central authority. It's distributed, decentralized, and it's designed to be offline first. So it will, work in cases where you have, disconnected networks, and you don't have necessarily the ability to be able to fetch a file from the other side of the planet. You might need to be able to get it from somewhere locally. It uses a unique and upgradable standard for referencing content. So you can think of IPFS as a little bit like a peer-to-peer version of HTTP, the protocol that we use for the web, for fetching web pages. But IPFS itself is not a blockchain. It's just, like I said, a protocol like HTTP, but it has some really unique features in it. So what is a good way of explaining this? We're mostly familiar with location-based or path-based content addressing. So that is, for example, files stored locally on your computer or accessed via the web. The address tells you where the piece of content is. But there's no way to know whether that expected content is what you're actually going to get until you fetch it. IPFS uses a thing called a content ID, a CID, and you have assurances that you're getting back exactly what it is that you've requested. You're getting the same material back regardless of where it comes from. So anybody that is serving up that same CID is serving up that same content. A colleague of mine, Dawn, came up with a really good way of explaining this. Let's say I go to the store to buy you your favorite box of cereal. I ask you, what do you want me to get? And you say, go to the grocery store, find aisle 6, third shelf along, 8 boxes along from the right. That's the box of cereal, right? That's location-based addressing. Now, even if I follow those instructions faithfully and accurately, it might be the fact that the content has moved. The box of cereal has been shifted overnight, the stock taking, they've moved it, maybe they're out, maybe a bored kid has gone around and shuffled everything around. You don't know necessarily whether from where it is exactly what you want. So let's try the content addressing way. So again, I ask you, what cereal do you want? And you tell me your favorite cereal is called Reese's Puffs. It's in a box that's orange. It has a picture of a bowl on the front. And the last numbers of the UPC code are 1256 for the 11.5 ounce box, or 5034 for the 29 ounce family size box, right? So now I know exactly what it is I'm looking for. I can go to the store, I can look along the shelves, I can look for the orange box, I can look for the bowl on the front, I can check the name and the UPC code to be sure that that is exactly the thing that I'm meant to be fetching, regardless of where it is in the store. It might even be when I come into the store that it's actually on a promotional aisle right at the front of the shop, and I don't even have to go to the cereal aisle to get it. It might be I can get it from somewhere much closer. So it's amazing that just shifting the focus from location-based addressing to content-based addressing both increases the accuracy and the verifiability of the data that we're fetching, but opens it up to massively distributed storage solutions. So as I said, you create this thing called a CID, content ID, and it's a bit like a cryptographic fingerprint. And IPFS uses a cryptographic hash function to verify that data and create this CID. Every CID is unique and is also the same size. So regardless of the amount of data that you're storing, you get a unique identifier that is of a known size. But importantly, this CID can be reproduced from the content. So when you get the content, you can actually reprocess it and see if you get the same CID. And if you do, you can be assured that the content you have actually been served up is the content that you asked for. So you don't need any kind of centralized service to authenticate what it is you're getting back. You know that you've asked for something, what you've got back matches that. So let's say we've got a folder structure, and each item has its own CID. It's arranged in what is termed a Merkle DAG. It's a tree of a number of items with hash described by hashes. Now say we want to copy biscuit.png down in the bottom, the little corgi, Filecoin corgi mascot, and I want to move it to another folder. Because the two copies, I don't have to copy the actual data, I just need to reference the CID. So what I can do is I can move the CID and put that somewhere else within that tree. And that allows us to do what's called deduplication as well. So within the network, we're not unnecessarily replicating the data multiple times there. Because the CID always represents exactly the information, unlike a location, then we're retaining the verifiability of that data or pieces of data. So one CID might represent that entire tree there. We have a root CID that encompasses all of the bits of data in, but each of those bits of data would also have their own CID. So it unlocks the decentralization aspect because we're no longer worried about where something is stored. We can just focus on what it is. So we can now represent content and store it, but how do we actually retrieve that content? So IPFS, you end up with a peer-to-peer network of nodes on the network, and each node, each peer has its own unique ID called a peer ID. And that is linked to a cryptographic identity for that node, and that allows the nodes to communicate with each other via a secure encrypted channel. Now, if you're a developer, you might have heard, well, you probably know what a hash table is as a developer. You've then got a distributed hash table, which is think of it like a directory, a global directory, in which you can look up a piece of content. And the main difference being is, unlike a regular hash table, this is spread amongst a number of peers. And there's a mathematical relationship between the content ID and the peer ID. So when you ask your node, fetch me this piece of content with its content ID, it doesn't necessarily have to broadcast to the entire network. It actually has a reasonable idea as to which nodes might have that bit of content. It can go and ask them. If they don't know, they will have their peers, and they will be able to say, well, okay, this other peer might have a better idea. So it's a lot more efficient than just broadcasting to the entire network. Some of this gets a bit technical, so if you want to have a deep dive, then I suggest check out, there's a site docs.ipfs.tech that has the full details about how IPFS works. But the main thing to understand here, amongst all this kind of big brain protocol, is that this is the functions that make IPFS work. And not just for Web3, and as I'm going to be talking about NFTs, but for the web in general. There's many different services that use IPFS. Think people like Netflix. There's Wikipedia on IPFS, for example, as well, that you can access. So it's important for people that want to distribute content in general and make content freely available to anyone. It allows trustless transactions between users regardless of any existing social or political trust or distrust. But how do we assure the permanence and the persistence of that data? Why would one of these random nodes hold that data for you? You know, let's be honest, they probably wouldn't do unless there was some, incentive for them to do so. So maybe you can just pay them to store their data. And there's services like that. They're called pinning services. One of the best well-known is one called Pinata. And you pay this service, and they will what's called pin that data, which means they will hold that data on their node. But we've kind of got back to the centralized problem that we're trying to get away from with things like pinning services. You could run your own network of nodes. It's actually pretty easy to run your own IPFS node. There's an IPFS desktop client, and you could run it locally on your laptop, for example. But one of the problems being is, at the end of this talk, I close my laptop, I walk off, my data goes with me, you can no longer access it, right? So really, you do need it to be spread around, and we need some incentive to encourage people to store that data for you. So this is where Filecoin comes in. So this is the second piece of the puzzle here. So I've talked about IPFS, and we're now talking about Filecoin. So Filecoin is a decentralized storage system. It's designed to leverage a crypto economic model to encourage the storage of that data and ensure the data is stored persistently, highly reliably, and most importantly, verifiably across the network. So similar to IPFS, you want to still be able to verify the data's there. So Filecoin currently has over 4,000 storage providers globally and makes up 1% of the world's current data storage capacity. So it's pretty big. It's the largest decentralized storage network out there. So let's dig into Filecoin a little bit. Filecoin is, I said, architected to use this crypto economic model, and you can determine the permanence of the data yourself. So whether you want the data to survive for 500 years or 5 minutes, you have total control over the permanence of that data. And also the resilience. How many copies of the data do you want stored about? Because we've got a crypto economic model in which people are rewarded for storing the data, but still, accidents happen or somebody could delete the data. So you want it to be stored multiple times. Now, the distributed nature of of Filecoin, actually means that it's very cheap to store data. So the average cost of storing 1 petabyte of data is about $4 a month on Filecoin. For reference, that's about 5,000 times cheaper than storing it on something like AWS. And it also has kind of internet scale capability. It's currently storing about 18 exabytes of data, which, like I said, is about 1% of the total storage capacity, and it's growing at quite a rate. This has only been done in the past about 2 years or so, and it's still growing. So to make all this work, Filecoin uses a storage deal that includes 2 main consensus mechanisms to ensure that the data is permanent there. So there's a reward system for good actors. So when a storage provider negotiates a storage, when you negotiate a storage deal with a storage provider and they store your data, they're actually rewarded for storing that data. And they have to provide what's called a proof of replication. That's a cryptographic proof that says they have actually stored the data. And then over time, they have to prove that they can still serve a random subset of that data, a thing called proof of space-time that they provide as well. And that's what actually drives the rewards that they get. So when they periodically provide this proof of space-time, they then get a reward from the network for storing that data. And so when a storage deal comes up for renewal, so like I said, you can define the length of time that a storage deal lasts for, and you negotiate that with the provider. When it comes up for renewal, you can then go and renew that with them, or you can let it expire. It's up to you, depending upon what you want to do with the data. But there's an efficient marketplace that's created by these Filecoin storage providers bidding on the data there, which is why the price is actually quite low, because there's this competitive marketplace in there. And in a bit, I'll talk about smart contracts and one of the things that we're working on that allows the automated renewal of these storage deals. So you also have sovereignty over not just the permanence here, like I mentioned, and you can have something like a smart contract. You can renew the deals over time, but also the redundancy of the data. So you can determine how many copies of the data are going to be stored. So IPFS and Filecoin are two different projects, but they're complementary. So IPFS offers the fast, flexible retrieval of data, and Filecoin offers the verifiable data persistence, so the long-term storage. The idea being that even if the IPFS node that you're pinning the data to disappears, Filecoin will ensure that it is still available and persisted long-term. One of the things to clarify is that IPFS is protocol agnostic, not protocol agnostic, storage layer agnostic. So you can actually use IPFS with centralized storage systems as well. So you can actually mix and match between things like Filecoin, which obviously we think would be a good way of storing data permanently, but also you could use something like AWS S3 as well. So moving on to the data and storing the data. So what I'm going to talk about today is one particular storage helper, as it's termed, that's built on Filecoin and IPFS, and it's called NFT storage. You can possibly guess what it does by the name. So it is storing NFT data immutably, permanently. And that's one of the main things that's integral to the whole value proposition of NFTs, right? So the whole non-fungibility aspect of NFTs works really well with IPFS, because you want to ensure that when you mint your NFT, the URL that you have in there references a piece of content, and that piece of content can't be changed underneath. With HTTP, it could be, whereas with IPFS, that URI is a IPFS URI with a content ID, and so you know it references exactly that piece of content. And if it was changed, then you would know. So NFT storage takes care of the kind of the nitty-gritty of both the IPFS side and pinning the data to multiple IPFS nodes, but also negotiating the storage deal for you as well on Filecoin. And it does it with sort of, I think it's 8 times redundancy on different storage providers. Currently, over 25 million NFTs are stored on NFT storage, and it's used by names that a lot of people know, like OpenSea or Magic Eden. It's currently operated for free by Protocol Labs as a public good, but we're working on a way of actually having perpetual storage deals run by smart contracts as well, so you won't need to trust a centralized party for dealing with that side of things soon. So how would you use this with the XRP ledger and XLS20? I've created a quick little demo for you. So I'm going to be storing my Xroom avatar on NFT storage, and then NFT storage will take care of, like I said, the pinning of it and the storage deal. So what's so great about this is that it's actually going to fit on 2 slides, the code that we need here. So First of all, we need to read the code from the file system. That's using standard JavaScript FS library to read the data from the file system. We're then going to store it on NFT storage. So we create an instance, instantiate an instance of the storage client. We pass in a API key, an access token that we get from the NFT storage website. When you sign in there, you'll get an access key. And we store the data. So we're storing a blob here, storage client.store blob. And so that's just storing the image data itself. You can also store metadata, JSON metadata, and it'll take care of that as well for you. But what we get back is the CID, the content ID, and we then construct a IPFS URI from that content ID there. That's it. That's your NFT storage taken care of in just those few lines of code. So moving on to the XRP ledger side, so I'm actually minting the NFT, sorry. You need to instantiate a wallet. So I'm instantiating a wallet here, connecting to XRPL Labs testnet, and constructing the transaction. So one of the great things with the XRP ledger, if you don't already know, with XLS20, you don't need a smart contract to store an NFT. Most other blockchains use smart contracts for NFTs. This example would definitely not fit on 2 slides if we had to go and construct a smart contract as well, right? They're considerably more verbose, and as David said in the keynote this morning, that's one of the potential downsides is that those smart contracts introduce an attack surface. There can be bugs in the smart contracts as well, whereas with the XRP ledger, it's native functionality. Oh yeah, and you see the IPFS URI in there that we constructed in the last slide. We submit that to the blockchain, to the XRP ledger, and away we go. So I've actually got this here. I can show you. Here's an account. You can see there's no tokens here. And what I'm going to do is I'm going to run my code here. And it's minting my NFT. So it's connecting to NFT storage. It's uploading it. It's connecting to the ledger testnet. And it will be minting the transaction, and success. And we've got back a URL there. Now, I think that's the same, should be the same as this one. If I hit search now, there we go. We've got our transaction, we've got our NFT, and if I click view, ta-da, there's our NFT. So that was it. That's the storage done there. So one last bit before I wrap up that I want to talk about is a project that I'm specifically working on, which is the Filecoin virtual machine. So this is now bringing smart contracts to the Filecoin network, and it is allowing us to add programmability into the network. So if you think of what I've described for Filecoin as being layer 0 here, the storage, then the next thing is doing computation over the state of the data. And so that's what the Filecoin virtual machine will allow you to do. So I mentioned we can have a way in which you could automatically renew those storage deals using a smart contract, for example, and remove a bit of the human element from the process there. You could also have things like data DAOs, in which you actually have multiple people potentially contributing towards the cost of storing it or voting on whether it's stored or whatever. And then layer 2, we've got another project on top of that called Bacalhau. And Bacalhau is an off-chain solution for actually doing processing on the data. It's actually slightly similar to Codius or Hotpocket on the XRP ledger that allows you to do that computation of data there. So what sort of things does this allow? This slide just has a number of kind of potential ideas that we can do. I've mentioned things like data DAOs already. So you can use that. Imagine if we could actually tokenize entire data sets and then use those. So rather than using the value being a currency, imagine the value being data itself, and you're actually tokenizing the data and passing those tokens around. You're creating effectively a dataverse, right? Rather than just a sort of a metaverse, you're creating a dataverse with that data there. And so, you know, the example I gave earlier, talking here about geology data, for example, you could actually do then processing and have that kind of run as a public good. So a little bit about the technicals of the Filecoin virtual machine. It's built on WebAssembly. It's WebAssembly core, very similar to hooks. And the reference SDK is built in Rust. We're also working on an Ethereum compatible version as well, the FEVM, the Filecoin Ethereum virtual machine. And that will allow you to run Solidity contracts on there as well, kind of out of the box. So where are we with it now? Milestone 1, we have it shipped and running. We've actually rewritten some of the internal functionality of Filecoin using the native what are called actors, which are the smart contracts in Rust. And we have on the testnet, we have the early beginnings of the Solidity, the FEVM, the Ethereum one. So that can currently run. It can run Solidity contracts. It runs a subset of Solidity contracts at the moment. And with each release, we're kind of expanding that. So that's a whistle-stop tour of IPFS and Filecoin and why you should use IPFS for your XLS20 NFTs. So thanks very much.